Okay, good morning. Thank you for your patience. I suppose there may be more people coming in as we go along. We'll get started. My name is Venu. I'm at the Indian Institute of Science. And today I'm going to be talking about this framework for doing motion averaging in 3D vision. And feel free to stop me at any point if you have questions about whatever I'm speaking about at that point. Okay, all right, so estimation of geometry of cameras, essentially camera motions, if you will, is a long-standing problem in computer vision. It's been around forever because, if you want to study the world, you want to know where your camera was when it took a picture. And so geometric representations, and not just in terms of cameras and camera forms, but of various kinds, have a big role to play in computer vision. But on the other hand, since we are building systems that are supposed to work with data, you also have a lot of statistical estimation issues that you have to worry about. And what we're going to be really looking at today is a set of problems which lie at the intersection of these two areas. There's been enormous amount of work in geometry on the one hand for about 2,000 years. And for a few hundred years, people have developed a lot of work on statistical representations for various problems. And it's only of late in the past couple of decades or so that in computer vision, we're beginning to be interested in asking questions about how do you do estimation on geometric representations of interest to us. In particular, our focus today will be limited to 3D geometry, and we're going to be looking at the question of how do you recover both 3D structure and motion given data. And the data can be of two forms. So you have the classical form of the structure from motion problem, where you have regular color images, let's say, taken with a pinhole camera model, which we will look at in a moment. And in more recent times, with the availability of depth cameras like Kinect and so on and so forth, you also have the ability to do 3D modeling using raw scans that are available. Okay, so we're going to be looking at both these forms. Okay, so just to reiterate, geometry is at the core of 3D reconstruction, and we are basically going to be looking at both these sources or both these types of sensors. On the one hand, you have regular camera images, and on the other hand, you have scanners which can give you direct depth representations. And because of the very nature of the difference in their geometric forms that they give you, the problems that you're going to be addressing are intrinsically different in nature. Okay, so let's take a very brief look. I'm sure most of you are very familiar with this problem, with the old question of how do you recover 3D structure given multiple images of a scene. So here you have a very large temple complex in southern India, and this is 3D reconstruction you can get from a standard pipeline today using about 2,500 images. So you can get very good quality geometric representations with free-form data acquisition, right? I mean, you can just walk around and take pictures, and this advance in structure from motion is essentially largely due to, firstly, a deeper understanding that was developed in terms of projective geometric representations of the pinhole camera model about 20 years ago. But there have also been great advances in both robust and development of both robust and efficient algorithms. And as we all know, I mean, data sets keep growing every day, as do conference sizes, I suppose. And you have the problem of trying to handle large amounts of data. So for example, just a few snapshots, you can see that a standard pipeline with you just take a bunch of pictures and throw it at the pipeline, and this is the kind of accuracy that you can get. It's very good, yeah? So just to reiterate, this is an architectural drawing I took out of a guidebook for the site, and this is the reconstruction that you can get, okay? And for pretty much for nothing in terms of the costs for the sensors, right? Just a regular camera. Okay, but where is the problem? I mean, what is the source of our problem that we're going to be dealing with? This is all old hat, but just for completeness, I'm just going to very briefly go over it. So essentially what you have is a let's say you have a pinhole camera model, which we are all familiar with from high school, right? So what you essentially have in the pinhole camera model is you take a point in the 3D world, and then you pass it through a transformation which represents the relative geometry of the camera with respect to your coordinate system. And K here represents the camera calibration. Throughout, we will just assume that it's calibrated. Yeah, we will leave that out of the picture for the rest of our discussion here today. Now, once you pass it through this, you get a picture. So, right, so essentially you have a point in 3D space, you trace a ray from that point through the pinhole, and wherever it intersects the image plane, that's where your image is, yeah? So this is fairly simple, and this is the source of a lot of trouble, because essentially it's a non-linear projection problem, right? So you lost a lot of information from going from the 3D representation to the 2D form. So how do we solve this? For example, the temple reconstruction that I showed you, the standard algorithm that has been around for a long time, going back to the photogrammetric literature in the 1950s onwards, has been to do with this idea of what's known as bundle adjustment. It's essentially something like a generative model. It asks the question, okay, I see these points on the image planes, and let's say I know which points are matched with each other across the images, and then I'm going to ask, where would the 3D points have been, and where should the cameras have been, such that it gives me what I see, right? You're just sort of doing a data fitting problem, right? So you want to minimize the error. That is, if you take a 3D point somewhere and you project it on a given camera, and you get a projection, and then you ask, well, where did I actually observe it? That difference is what you want to minimize in some sense, yeah? So it becomes a data fitting problem. It's very well known. There are all kinds of algorithms for dealing with this. So essentially, it's the standard approach to this problem has been to use a highly nonlinear minimization. So this is basically because you're looking at a projection model, you're going to get ratios of the unknowns that you're trying to solve for. And that makes it highly nonlinear and extremely high dimensional. Imagine when I'm talking about a few thousand cameras and maybe hundreds of the order of fractions of millions of points, then you have an extremely high dimensional problem, and you want to do a optimization over that. Yeah, did you have? Come again? D is just sort of your measure of the fit, right? I mean, it's a general function. Usually it's the reprojection error. People just take least squares, right? But if the distance metric? Yeah, it's just a metric. It's just a metric which compares where the observed image feature point is and where you expect, where it should be if you had projected it correctly, right? And so you want to sort of minimize it. It's like a data fitting problem, right? I mean, imagine you have a bunch of points and you're fitting a line through them. Given your parameterization of the line, you know where the point should have been on the line, and you know where it is, and you want to minimize that distance. So this is something of that form, but except that it's highly nonlinear. Okay? And so now, there's been very impressive methods for actually solving this optimization, which is, for example, the temple reconstruction that they showed you is one such case. And it's essentially built on using incremental approaches. So the approach that people took is they said, look, we can't take 2,000 cameras and solve the entire highly nonlinear optimization in one go. There's just no way it's going to work. As you know, in any nonlinear optimization problem, you need to have a pretty good initialization, and then you have to worry about what is the nature of the energy landscape that you're working with, right? And it's kind of hard to get a handle on both when you have this extremely large high-dimensional problem to deal with. So the way people addressed it is they said, we're going to do it incrementally. So we'll just grow the solution. So you start with a few cameras, and then you keep adding one at a time or a few at a time, and eventually get to the final reconstruction. It works well, but the problem is it cannot recover from certain errors. It does not have a global view of the problem. So let's say you start somewhere, and you take a new camera. It has no relationship with the existing set of cameras that you've solved for, so you don't know what to do with it. You don't know where to place it. So typically, these methods tend to throw it away, right? Because you have lots of images. You don't care about solving for every camera in your solution. So it does not have a global view of the entire data set that you have. And that's a huge limitation apart from the computational complexity of these things, which is enormous. Okay, it takes a lot of computational work to actually minimize an objective function of this sort. Okay, so just to reiterate, so the key problem in structure from motion is really this, that there is a nonlinear interaction between the 3D structure and the motion of the camera, because that's where the projection is coming from. And in a sense, the image projections that you see, the feature points that you see on the image plane, are now sort of an entangled representation of the structure and the motion, right? And that's the source of the problem that we have to deal with. So now let's take a step back and ask, what else do we know from projective geometry, for example? So in projective geometry, it's a standard result in multi-view geometry, and you can find it in textbooks now, is that essentially you can take two cameras, just two, and write an algebraic representation of the relationship between the feature points and the camera geometry. Okay? So you can write a representation of, you can write a constraint, an algebraic constraint that needs to be satisfied by the observed image feature points, the matched feature points, and the rotation, let's say the rotation and translation of the camera pair, the relative rotation and translation between a pair of cameras. And the key point here is that this is very fast. Solving this is essentially a trivial linear problem, more or less. And the advantage it has, as I hope you can see, is that the structure, the actual 3D location of these feature points does not play a role in this representation. You obviously do need points for projections. To be able to observe matching points, you need 3D points out in the world, but you don't solve for the 3D representation at all. So this representation, so the so-called epipolar geometry between a pair of images, is independent of the actual 3D structure. Okay? And that's a huge advantage, because now, remember, our original problem with the pinhole model was that these two things were mixed up. Structure and the camera motion was mixed up. But here, at least in the case of two cameras, in the minimal case of two cameras, you can eliminate structure and work with it. So it's very fast, but obviously it's not very accurate because it's an algebraic representation which does not quite fully capture the properties that you're interested in. Okay, so you have this contrasting sort of scenario. On the one hand, you have this bundle adjustment or large-scale optimization. It can work with many images. It's very accurate, but it's extremely slow, and you need to do lots of things to make it work. On the other hand, the algebraic approaches that epipolar geometry, for example, represents, works with few images, is fast, but it's not very accurate. Okay? So the question that we are interested in, the original motivation for doing motion averaging for me was to ask the question, how do you extend this idea of eliminating structure from the structure from motion problem, right? So you have a problem where you have these two entities, the motions of the cameras and the world, the 3D structure of the world entangled together. Can we do something to factorize the representations so that the structure is completely eliminated from the problem and you're just working with the motion representations? And as we will see in the remainder of this tutorial, this gives us a lot of different advantages. It gives us nice geometric structures to work with, and you can do very useful things with it, both in theoretical terms, but also in practical empirical terms. Okay, so what motion averaging essentially now it translates to is that you convert the problem to one of camera estimation alone, and you essentially factor structure out from the problem, and it is formulated in terms of a graph representation. So before we proceed, I'm not going to spend really any time on the pipeline. I want to emphasize that what I'm talking about is only one part of a very large pipeline that you would need to have set up to be able to actually solve the 3D reconstruction problem, right? You need ways of, just to have everyone on the same page, you really need ways of matching features. I haven't told you how to do that, but that's an important part of the problem. How do you match features across images? And then how do you get, in our case, as we will see, we are interested in solving for the geometry of pairs of cameras. And then what we tend to do, now there are variations, but a typical way of addressing the motion averaging problem in pipelines is that you first solve for 3D rotations. You do the averaging on 3D rotations, and then you deal with translations. So remember, if you want to know the Euclidean representation of each camera in a global coordinate system, you need to know the Euclidean transformation with respect to your frame of reference, the Cartesian frame of reference that you choose. So you need to know both a 3D rotation and a translation. And we tend to solve for rotations first and translations later. And there's a specific reason for that, which will be obvious as we go along. Once you solve for the cameras, remember in this framework, we have eliminated the role of structure till now. But once you solve for the cameras, you can actually essentially triangulate backwards. Let me just try and, so for example, let's say I have now solved for where these two cameras are. I can shoot these rays backwards going outwards from the camera, and wherever they intersect, that's your triangulated solution. There are issues with doing that, but that's in a sense what we are interested in doing. Now there are many variations, and I just want to remind you that the so-called bundle adjustment approach for solving structure of motion is in theory optimal in terms of the minimizing some meaningful cost on the reprojection error. What I'm going to present to you is essentially a fast way of getting very close to that solution, but it's not the optimal solution in the sense that we want. So what you do is once you take the solution that the motion averaging framework gives you, then you use that to initialize the final bundle adjustment step. You just do a refinement at the end. But these are sort of details that can vary across pipelines, and we're not going to spend any more time looking at that. We'll focus essentially on this business of figuring out what the rotations and translations are. I mean, that's what we're going to do for the rest of our time today. Okay, so let me just repeat to reiterate what we are trying to do here. What we will show is that unlike the incremental approach for doing bundle adjustment, it is possible to do a batch approach for camera motion estimation, which is what the framework of motion averaging allows us to do. And it gives us a global view of the problem, if you will. And what it effectively does is it distributes the errors more uniformly than incremental methods. Imagine you take a camera and you just sort of walk somewhere and you come back, right? A typical robotics with the so-called SLAM context, right? So now if you're going to do just an incremental solution, at every step you're going to make some errors in your estimate, and they're going to just add up, right? So you'll have a drift in the solution. This is well known in the SLAM context. Yeah, so you have drifts in the solution, and when you come back to your original position, things don't line up anymore. Things are not consistent anymore, right? But when you take a batch view of the problem, that's eliminated. Okay, so you don't have that particular issue. So you have a natural way of accounting for loop closures, and you avoid many of the pitfalls of incremental methods. So some of the requirements we're going to demand of motion averaging is that it's robust to outliers, and we will spend a fair bit of time looking at the question of robustness today. It's fast and scalable. So as you have more and more cameras, you want to be able to scale, and it has to be as accurate as you would like it to be. And I also will, time permitting, will show you how the same framework that we're going to develop for doing structure from motion kind of problems with regular cameras can be extended or directly applied to 3D scans and alignment of 3D scans for building large-scale reconstructions of 3D scenes. I want to point out that there is actually, interestingly enough, this problem or this question rather, is an old one. So there are people who look at the questions of time synchronization on wireless networks. This is just as an aside, right? There are other domains where this applies. So if you have a network of sensors operating in a communication kind of environment, they all have their local clocks, let's say. And you want to synchronize the clocks of all your sensors so that then you can make meaningful measurements. So the synchronization problem that they deal with is in principle the same as our problem, okay? The underlying representation is different. They have a scalar which is just a timestamp. The time delay between different clocks is what they are trying to solve for, okay? And but it turns out that this is the underlying problem is actually identical, okay? And you will find lots of papers in the literature using the term synchronization instead of averaging. I use the notion of averaging, the term averaging rather, when I first wrote papers on this a while ago, simply because for me it was just taking many measurements and taking some sort of a meaningful average of them. But there are others who are coming in from this particular context, so you will find the term motion or rotation synchronization, and they mean the same thing as what we do here, okay? And there's also the classical multidimensional scaling problem, which is more or less, it's similar in spirit. Okay, let me just very quickly go over what we are going to do before I actually launch into the actual motion averaging representation. As we have seen, we have now noticed I've eliminated K. The camera calibration is out because I'm going to assume that it's known. So the typical so one way to understand what's happening when you take a picture is you have a 3D point in its projective form, you pass it through a Euclidean representation of the camera motion, and then you pass it through an ideal pinhole camera, and that's your picture. So all of this has very nice geometric representations, it's a projective mapping, all of this is well known, but it so turns out that the underlying geometry of the camera motion, which involves a 3D rotation, a rigid rotation and translation, also has very nice geometric structure that we will exploit as we go along. Okay, so the same kind of questions, before I move ahead, I just want to point out, as I mentioned a little while ago, the same kind of issues arise in 3D reconstruction. So imagine, this is like a standard well-known data set, but imagine this is a plan view of an object, right? Imagine you want to build a 3D model of an object. Now, no single view is going to give you the full representation. You need to have a 360-degree view of the whole scene, right? And therefore, when you take scans, when you build scans, you're going to get individual partial representations of the object that you're trying to scan or the scene that you're scanning, and then you want to be able to stitch them together, right? And to do that, you need to solve a problem of figuring out what is the relationship between the coordinate system of each individual scan with each other, right? So you need to know how to represent the individual motion. So it's essentially the same problem as we have in the other case. So whether you have a regular color image camera or a depth camera, the underlying question of figuring out the Euclidean geometry is the same. Of course, the nature of the data that you're going to get from these two representations is intrinsically different. Therefore, your approaches of solving the problem will be somewhat different, okay? But the essential question is still the same. You have, effectively what you have is, every time you take a picture or you take a scan, you have a partial snapshot of what the overall scene is like. And to get a full picture of what the scene looks like, what you need is to be able to relate the relative geometry of the individual cameras. And that's what we're going to do in motion averaging. Okay, so I showed you this pinhole camera model. And in 3D registration is much, or in the case of 3D scans, it's much more straightforward. You have a point in 3D, and then you apply a Euclidean transformation, and you get its corresponding point in 3D in a different coordinate frame of reference. Okay, so essentially M, which represents the rigid Euclidean motion, is composed of a rigid rotation, or rather a 3D rotation, and a translation, and all of them have specific geometric structures that we will utilize. Okay, before I go ahead, this is a minor point. At this point, this is the first time you're looking at it, it doesn't matter. But when you read papers, it matters a lot. Now, we know that if there's a rigid transformation between two sets of points, let's say, then there is a Euclidean representation that will match the two, but the representations vary. Some people apply the rotation first and then apply a translation, right? So if I want to move something, I can first rotate the object and then translate, or I can translate the object and rotate. They're equivalent, but they're not equal, right? So you can find the relationship between the two forms, and now what happens is you get slightly different looking equations in papers, and it's a source of confusion. I've had students write to me once in a while saying, I tried this and it doesn't work, and so on and so forth. And this is a source of a lot of confusion. The other important point to remember is oftentimes you find this, people are not very careful in specifying. If I tell you the motion between object A and B, I need to tell you whether I'm moving A to B or B to A, or in this case, I to j or j to I, and it matters, right? And if you're not careful, then you will have problems in trying to work out the representation that you're looking at. Okay, having said that, now we can look at the basic underlying representation for doing motion averaging. So what you will do is we'll start with a view graph. So you have a view graph, which is nothing but a graph where the vertices represent cameras, and the presence of an edge between two vertices essentially says that you have a camera-camera relative motion available. That is, you can solve for the relative motion between two cameras. So imagine now, let's say I take a camera and I just sort of walk around this room and I come back. Now what's going to happen? Cameras that are, or images that are close to each other in time are essentially looking at the same part of the scene, so I can actually solve for their relative geometry. But obviously, if I take a picture here and I take a picture there, there is nothing in common that I can use to relate the two camera representations, right? So in a sense, when I have an edge in a graph of this form, in the view graph, the edge is signifying the fact that I have enough information available to be able to solve for the relative geometry between the pair of cameras that are represented by the corresponding vertices. So now if I want to describe, so what is my objective here? Remember, my objective is to solve for the full 3D motion of all the cameras. In other words, I want to be able to assign a motion value to every vertex, because each camera is a vertex. So I want to say this vertex has a given motion with respect to my global frame of reference, right? So I have n cameras. Now I can pick, any one of those cameras as my origin, if you will, right? As the origin where I place my global coordinate system. So once I do that, I need to specify the motion of the remaining n-1 cameras. So I need to solve for n-1 motion representations given n cameras, right? Now, in a sequence or in a set of images, if you have a full or a complete graph, then you have as many as n choose 2 such pairs available, right? So you have n choose 2 edges or n choose 2 relationships in the data, yeah? In practice, you don't have all of them, but in theory, you could possibly have all of those relationships available. So essentially, you have a problem where you have as many as n choose 2 or order n squared observations, and you need to solve for n-1 motion. So you have an order n problem. So what you have is a highly redundant system of equations that you're going to solve for. Okay, that's the point that I'm trying to make. That you have many, many more observations, or you could potentially have many observations that you can use to solve for the camera estimation problem that we are interested in. Okay, so let's do a very simple, trivial exercise. So let's assume these are, VIs and VJs are scalars or points in some vector space. So let's say I give you the values of VIs at every vertex. Then, obviously, the value that you would assign to the edge would be Vij, which is nothing but the difference of the two vertices, let's say. Okay? So that's trivial, right? So if I tell you the values of the vertices, then solving for the values on the edges is trivial. It's just the difference between the two values on the corresponding vertices. The problem that we have in motion averaging is the converse one. That is, I give you the values on the edges because I'm telling you what the relative motion between two cameras is, and I'm going to ask you what are the values on the individual cameras, right? So it's like I give you the values on the edges, and I'm asking you what are the corresponding values on the vertices that are going to give me these values on the edges, right? Yes?
Can you please repeat what are the edges represent?
So the vertices represent cameras, and in the sense that each vertex is representing the motion of the camera with respect to some frame of reference. I pick some frame of reference. Now, so my problem is one of solving for the motion of every camera, right? So what does that mean? That means that if I pick a frame of reference, for every camera I need to specify, let's say, its 3D rotation and translation with respect to the frame of reference. Okay? So the vertices represent the camera motions. Now the edges represent their relative motion. And we'll come to the notion of relative motion. If you recall, we did this when we looked at epipolar geometry. I said that you can actually recover the relative motion between two cameras very easily. And that's where it originally comes from. But at this moment, for the moment, let's just focus on the vector space case. It's very trivial, and then we'll come back to me if you still have a question at that point. So I hope you recognize that in the case of vector spaces, or if you just think of these as scalar values, right? Forget about cameras for the moment, right? If I have a scalar value at every vertex, and I put the difference on the edge, right? Yeah? Now, the problem that we have in our case is conceptually the following, that I give you the values on the edges, I give you the differences, and I'm going to ask you, what should the values of the vertices be, right? And so this is, of course, a trivial problem, as I will show you, and the same principle extends to solving for the case where the values on the vertices is not a scalar, but actually the camera geometry representation that we're interested in. Okay? So you can think of the motion averaging framework as consisting of two things. You have a graph which tells you what is the relative relationship between cameras, and you have a geometric representation that you want to assign to each vertex, right? Each vertex needs to be assigned some geometric form that is of interest in the problem on hand. Okay, so what's the basic idea here? The idea here is that you could take relative displacements and assign them to edges, right? So Vij is nothing but Vj minus Vi. Or in other words, if I go around in a loop, we all know this, right? You take vectors, you add them up, and you come back to your original location, the net displacement vectorial sum is 0, right? That's a constraint that's inherent to the form that you have. Yeah, so in our case, our loop could be of this form, Vj minus Vij minus Vi, which is essentially you just traverse a loop, and they should all add up to 0 in this case. Okay, so the effective transformation is 0, and what it basically means is that now if I'm going to give you values of Vij's on individual edges, then this constraint has to be satisfied by any solution that you propose, isn't it? I start with Vij's on the edges, and say, let's say you give me a list of VIs that you think is the answer for the problem, then your VIs and my Vij's should satisfy this relationship. If I traverse, I should come back to where I was. Yeah? So I'll come to this bit. So essentially, it gives you a strong constraint on the set of solutions that are admissible. Okay? You can't have any solution because any solution that you propose has to satisfy this simple basic constraint for every possible loop. You could also think of any loop through this graph, right? Any cycle on the graph, rather, and that should satisfy this relationship. Okay? Now, it gives you a strong constraint, and there's also an issue of a shift, and I'll come to this in a moment. Maybe I'll just mention this. So let's say if I tell you Vij is 5, let's say, it's a scalar value, it's just 5, and somebody proposes a solution for Vi and Vj, let's say, 7 minus 2. But you can always add a constant to both of these values, and it would still be consistent with this solution, isn't it? Yeah? Because since I'm taking, think of what happens when you do integration in elementary calculus, right? I mean, when you do integration, what are you doing? You're taking all the differences and adding them up in some sense, but then you always have this constant of integration, because anytime you have a constant value, when you take differences, that constant disappears from your derivative, right? And there's no way you can recover that unless you know something else that's external to that representation. It's in that spirit. That is, any solution that is valid, if Vi's is a solution that is correct, then I can add a constant to all the Vi's, and that would still be correct, right? Okay, so there is this notion of gauge freedom, and this comes up in many cases. So think of geometrically, imagine the following case. If I were to take two pictures with cameras which are taken in this position, and I have the world out there, if you give me a solution, then I can say, well, what if I were to rotate them rigidly and also rotate the object? Can you tell them apart? You can't, because the projections are going to look the same. So there is essentially an underlying degree of freedom, which is essentially the so-called gauge freedom. It occurs in physics and in many other contexts, which is always the case. So what we will do is we will need to fix our coordinate system somewhere to be able to avoid this gauge freedom problem. Okay. So typically in most scenarios, you would just fix one of these vertices as the origin. So you just say that's my origin. Yeah. Because I could put my, in any coordinate system representation that you have, you can put your, the basis, if you will, which will represent, and your Cartesian frame of reference, you can put it anywhere you wish, right? That's arbitrary. Your frame of reference is arbitrary, right? So you can just conveniently pick one of them. So now, let's look at this equation. So you have, for every edge, you have one constraint on your solution, isn't it? Yeah? And I said that I have n minus 1 unknowns because I fix one of the cameras. I have n cameras or n vertices. I fix one of them. So the remaining ones are unknowns. So I need a minimum of n minus 1 relative motions to be able to recover my underlying solution, right? But will any one of them do? Will any set of those edges work? The answer is no, because if you think of this as a graph, what are you doing? You want to specify the value at every vertex. How would you do it? If I fix, let's say, this as the origin, how do I specify this value at this vertex? Well, I can add up these edges, right? Yeah? So essentially, I need to be able to traverse the graph. I need to have a single connected component in my graph, right, at the very least. I need to be able to start at any vertex and reach any other vertex to be able to give a global solution. Yeah? So in effect, what you need is you need a constraint where the edges should contain a spanning tree. Okay? And that's the minimal requirement that you have. Obviously, we want more edges than a minimal spanning tree for our problem. Why? The reason is because individual edges are going to be noisy, right? They're all going to have errors, and we want to have more observations so that the overall fitted solution is going to be better, right? Yeah? Okay, so I talked about this problem of having noise in individual edges. So the problem is that if I have errors in individual observations, so the Vij's are coming from some estimation that you're doing of the relative motion between these two cameras. So if I take these Vij's and try and do this traversal business or go around loops, they are not going to add up. So you're not going to be able to find a solution that is consistent in this form, right? So think of your standard least squares problem, right? Ax is equal to b. Often, if you have a redundant system of equations, you'll seldom be able to find an x that is exactly going to fit the solution, fit the problem, right? Where the fitting error is actually 0. We're going to lose the top though, yeah. Okay, thank you. Okay, so this problem of the presence of noise in observations, which is inevitable, basically means that your observations are not consistent with each other. In other words, in a noise-free case, if I start here and I move this down, move in this path, or I take any other path and reach this vertex, the solution should be the same. The sums of those individual displacements should be the same. But obviously, in the presence of uncorrelated noise in each one of those edges, that's not going to be true anymore, right? So if you take different paths, you're going to get different answers, which is a problem. So what do? You find the solution which is most consistent with edges. This is the typical thing that we do when we do a fitting exercise, right? When you take many inconsistent relationships and try and find the best possible solution. So typically, let's say a least squares, that's what a least square solution is doing for you, right? It's trying to say, look, we cannot have a single solution that is exact with the constraints or observations that we have. So we'll do the best that we can. We'll find something that is the best solution according to some metric that I define. Yeah? Okay, so that's what the least square solution in this case is going to be trivial. So for example, you could just do this. So take this relationship. Now look at this. This is nothing but, this is saying the difference of the individual vertices is the value on the edge. The left-hand side is the unknowns. The right-hand side is the known values, right? I'm giving you Vij's, the values on the edges, and I want you to tell me what Vi's look like. I can write this individual edge relationship as a dot product of this form, right? And once I do that, I take the relationship for every edge, set up a system of equations. Essentially, it's of the Ax is equal to B form, right? So A times the unknown values, the individual vertices, should be equal to the values of the edges that I observe, okay? And so this is, A is nothing but the graph incidence matrix, and it has other roles to play because, as we will see in a moment, there is the graph Laplacian. Anytime you want to understand graph structures, there's a graph Laplacian lurking somewhere, right? So because that's a very powerful way of analyzing what a graph is telling you. So it's related to the graph Laplacian structure. And if you recall the gauge freedom problem that I mentioned earlier, you will see that it's quite obvious from here. If I have A times V, this is equal to A times V plus any scalar times all ones. If I add a constant to all of those values, because I'm taking, there's a 1 and a -1 in every row, so the scalar value S will just cancel out, right? So that's where the gauge freedom is, yeah? So we can fix that by picking one of those things. Now we can come to the question that this gentleman here was asking me about. What do those edges represent? Obviously, we are not interested in the scalar problem. I just set it up to motivate the underlying the issue that we are interested in. What we want to do is we want to assign individual camera matrix values to the vertices, because each vertex you want it to represent a Euclidean motion with respect to some unknown frame of reference. So the edges in this case are now going to denote the relative motion, which analogous to the scalar case of the difference in the matrix form would be of this form, right? So now Mij is going to be Mj times Mi inverse, right? That's the matrix analog to taking the difference between those two values, yeah? So essentially you have the same problem again. You have left-hand side is the global motion that you want to fit. You want to get all the Mij's, which is as consistent as possible with these relative motions, Mi's, as consistent with these relative motions, Mij's, right? So if I say Mi with a single index, it is representing the camera or the vertex. A pair Ij is representing the edge, okay? Right, so I can just set up a linear system of equations of this form. Notice I took this equation and just rewrote it in this form, right, where I have a whole bunch of m's, which are the unknowns. I can get another linear system of equations, and I can try and solve it. The question is, can I take a linear solution? So if I have, in this case, a b times mg equal to 0 problem, it's nothing but a null space problem, right? Yeah? So I should be able to solve it in that form. Unfortunately, I cannot do that because the individual m's are not points in vector space of some dimension, right? They have geometric structure. If you think of a 3D rotation, what is a 3D rotation? You have a 3 by 3 matrix with 9 entries, but it has only 3 degrees of freedom because it has to satisfy all the orthogonality constraints, right? Yeah, so essentially, you cannot, so if you were to just solve this as a linear problem, you're treating these motions as sitting in some vector space or of some dimensionality, right? So obviously, that's not going to be a correct, valid geometric representation that we are interested in, because the geometric form of individual motion groups or motions are essentially nonlinear. They have nonlinear geometric constraints that they need to satisfy, and they form what are known as Lie groups, and we will utilize the geometric structure of the Lie groups as we proceed. Okay, yes?
So I did not understand why you solve this system of equations you solve the problem. Why don't you, if you solve it linearly?
So think of this as, let's say M's represent 3D rotations, okay? Or even 2D rotations, let's say, the standard form cos theta, sin theta minus. So if you solve it linearly, you will get, essentially you can solve it linearly and you can reconstruct a 2 by 2 matrix that's supposed to be the rotation. But is it going to satisfy the orthonormality constraints of the rotation matrix? It will not, because you've not treated them as, when you set up the problem as a linear form, you're not imposing any of the geometric relationships.
Okay, so you need to add more constraints to this.
Right, so you need.
The system of equation does not represent the two parts.
Right, it does not represent the true problem, because so I'm leading up to the form that, I started out with trying to motivate the vector space analog, which was VIs. That was easy to do. That would work with something like this. And I'm trying to just motivate the fact that you cannot do this at this point, that's all I'm saying, that you cannot do the same thing that you did earlier. You can't just get away with doing linear algebra, otherwise we wouldn't be all sitting here, right? So, yeah. Okay, any other questions on this? All right, so very quickly, so unfortunately we will, don't have time to do the geometric structure of groups, but I need to motivate it to some extent. So we have essentially stated that the motion forms that we are interested in are what are known as Lie groups, and they have specific geometric structure to it, which is very useful for our problem. And just to motivate this, so this is a caricature of an enormous volume of literature in mathematics on Riemannian geometry, right? So pardon me for that, but just for the sake of some kind of completeness, essentially we are no longer dealing with linear forms anymore, right? So you have your solutions sit on some nonlinear space, okay, in some sense, okay? And so you have a nonlinear surface within quotes embedded in some in some vector space, okay? And so the standard thing you can think of is points on a sphere. So if I tell you that a vector has unit length, then, and you solve, let's say you solve a linear system of equations, that's not going to impose the unit length constraint on the vector, right? So you're not going to be on the unit sphere anymore. You'll be somewhere else in that space, okay? So if you want that constraint to be satisfied, then you need to work on the geometric representation that you are interested in, right? So this is essentially, you want to work with the intrinsic geometric form. That is, you want to move, when you're solving for something, you want to move on the geometric representation, on this surface, if you will. Now, the trouble with any nonlinear form of this kind is that you cannot have in vector spaces, you can fix a Cartesian coordinate system frame of reference anywhere you want, and you're done. And you can represent everything in your vector space with respect to that choice of your coordinate system. You can't do that anymore with nonlinear forms. So imagine you're here on a sphere. Well, locally, if you take a local tangent space approximation, locally it's flat. So you can assign a local coordinate system to represent points there. But that representation is not going to be valid here, right? So you need some geometric mechanism of relating these two things, okay? So there's a lot of stuff that is done in Riemannian forms to be able to do this in a meaningful, geometrically consistent manner. And I'm not going to go into working too much. I'm not going to enter into too much of a discussion on this, but the basic point to remember is that if you have a nonlinear manifold, then you have to necessarily worry about looking at local coordinate systems. So when I'm looking at an epsilon neighborhood around a point, I can work with it as if it were a vector space, but I also need ways of relating these individual local representations as a move on the surface, okay? So, and what is important in this case is that the local vector space is equipped with an inner product, and once you have an inner product, you can define the notion of the length of a curve, right? So if I give you 2 points in some space, and I define a inner product that induces a distance metric, and I can compute the lengths of individual paths, And the notion of a geodesic that many of you would be familiar with is nothing but saying the path that has the shortest length between 2 points, right? So in vector spaces, they are just straight lines because vector spaces are curvature free. They are no longer straight lines in our representation form, yeah? So we have to worry about what they mean in our case. Okay, so in general, computing these geodesics on nonlinear Riemannian manifolds can be very hard. Oftentimes, you don't have closed form solutions at all. We are lucky that for the kind of motion representations that we are interested in for finite dimensional Lie groups, it becomes much simpler. So therefore, we can work with it fairly easily. Okay, so I said that I introduced this, an elementary notion of what a manifold is, without going into too many of its details. I'm sure we are all familiar with what a group is, right? So a group is basically nothing but a set equipped with a particular operation, and then that operator has to, the operation of those elements, the operation on elements of the set have to satisfy these properties, right? So, so think of addition on the real line. So then, x plus y has to be also an element of the same set. Associativity has to be satisfied. And the key element for our purposes is that there is an identity element for every group. And there's also correspondingly, that induces this notion of an inverse in the set, right? So this is pretty standard. And you can think of various kinds of groups that you can have. So you can think of the real line with the addition, just the summation, just adding 2 numbers as the operator. You can do modular arithmetic, and it'll still satisfy these forms. And of interest for us are matrices, which are square with this should be actually, So square matrices with non-zero, with positive determinant will also form a group, right? So if you think of say, if I take 2 matrices which have positive determinant, their product will also have a positive determinant. They will also be a square matrix of the same size, and so on and so forth. Okay? And so there's an enormous literature on the notion of representation and classification of groups. We are not going to go there. So in summary, the reason we are interested in these ideas is the following. You have a Lie group is a special type of a Riemannian manifold, because it also satisfies both. It's both a manifold, but also has group structure to it, right? It has both these properties. And so essentially, it has a nice sort of smooth differential structure. You can do calculus on it, right, on the Riemannian form. But it also has the group properties. And in combination, it gives you lots of special things that we can use in an efficient manner. And that's going to be key for much of what we will do in our motion representations. Okay. Right, so let's just take a moment and look at this business of, so we are interested in the specific types of Lie groups called matrix groups. So essentially, we are looking at square matrices. So let's say X is of size n by n. In general, it's typically denoted as GL of n, general linear group of dimensionality n. That's the terminology. Now, it's obvious that if I take their product, that'll still be a square matrix of this size. Associativity holds. There's an identity too, right? There's the identity matrix exists in this set. Okay. Now the question is, so essentially X sits in R n squared, right? N by n values. So if I take any matrix of size n by n and open it out, it's just going to be a point in vector space of dimensionality n squared. The question is, are all points in R n squared in this set? And the answer obviously is no, because you also need an inverse to exist. You need the matrices in this set G to be invertible, right? So you can, so you have this requirement that the determinant of X is non-zero. Yeah? So without that, so essentially what that translates to, just for the sake of completeness, is that the set of matrices of size n by n, which are singular, form of an algebraic variety. And essentially what you have is you take this vector space and you remove that particular part of it, right? So you remove, essentially, think of it as just removing all points which represent non-invertible matrices. And what remains is the set that we are interested in, right? And that's an open set in this form, okay? So we're not going to have to worry too much about the algebraic forms here. That's not of great importance. You can also now take, excuse me, you can also now take this group, which is the general linear group, and then specify some special constraints. So let's say now I say I'm only interested in matrices which have determinant 1, right? In general, it can have any determinant value. I'm only interested in matrices which have determinant value 1. So you'll notice quickly that that set of matrices with determinant 1 also forms a group. Just trivially, you can see that if I take their product, then their determinant will also be 1. So they form in particular a subgroup of the general linear group. And this is, in the literature, is known as the special linear group, SLN of n, okay? And we will now take this group and ask, so you can actually now start looking at group structures which satisfy specific properties. Another standard way of understanding group structures is to ask, or understanding the geometry of these group structures is to ask the question, what properties of spaces remain invariant when you apply these transformations applied from the, when you use elements from this group to apply transformations. So that's a standard way of understanding the nature of groups. So for example, you could take, you could ask the question, what kind of group elements leave certain properties invariant? In our case, let's say you want to leave the dot product invariant. The dot product of two vectors is of this form, and I'm going to say, well, if I apply a transformation to that space, if I apply M to all those vectors, I get a new dot product, which is of this form, and I'm going to demand that these two values be the same, right? And this is equivalent to saying distances are preserved, right? So if you say, find me a set of transformations where distances between points are preserved, right? So that's going to impose some constraint on M, right? You cannot pick any arbitrary M for this relationship to be true. Yeah, M has to satisfy some constraints, which is of this form. Yeah? And this, I hope you'll immediately see, is essentially your orthonormality constraint that you have. Yeah? So the only set of transformations that are going to leave your distances between points invariant are going to be orthonormal transformations. In particular, if you look at the real space, then they are orthogonal groups. So this set of matrices now is what is essentially an orthogonal group. And so you have the relationship M transpose M has to be an identity, which simply implies that and since both of them have the same determinant, what you get is a relationship of this form. Remember, we started out with things which have determinant 1, right? Yeah? Or rather, well, anyway, so let's not worry about that. Let's look at this particular form. So you have this requirement. And if you want this requirement to be satisfied, what you will see is that the determinant of M has to be either +1 or -1. Right? It's only then that you will have this particular relationship satisfied. Okay? So, so this group or the subgroup of the original general group that we started with is now essentially has two components to it. One set is where the determinant is +1 and one is -1, and they are not topologically connected. Okay, so they are like two sort of disconnected components. And by convention, we pick ON plus, the one with the positive determinant of +1, and we call that the special orthogonal group of dimension n. And this is nothing but the set of 3D rotations. So if you think of 3D rotations, what is the constraint that we know? We know that R transpose is identity, right? Now, when we say R transpose is identity, we in general, don't think about what the determinant of R should be. I mean, it could be minus 1, 2. But by convention, we don't do that. We pick the set plus 1 because that otherwise it involves a reflection. Okay? So now throughout, we are not going to revisit this part anymore. Throughout, we're going to be working with SON. In particular, we are interested in SO3 of dimensionality 3. We are interested in rigid 3D rotations. Yeah, any questions at this point? Okay. Right. There are a couple of other things that we are interested in, or of certain properties of groups that we will use. These are essentially what are known as group actions. And there are, in particular, two types of group actions that we're interested in. One is the product of two elements of a group that maps, this is a mapping which takes two elements from two groups and maps to the same group. So a standard example would be 3D rotations. So if I take two 3D rotations, multiply them, I get another 3D rotation, right? And there's another group action which acts on a different space, or in this case, a group on a manifold. And in our case, an element in SO3, a rotation, acting on a vector or a point in R3, right? So if I take a point in R3, apply a 3D rotation to it, well, I get back another point in R3, right? So I go from G cross X to I go back, I get a point in X, right? So these are the two kinds of operations that we are going to be interested in, right? So there's this business of the Lie algebra that we are interested in. I'm just trying to keep track of time, so we have to take a break at some point, right? Yeah. Okay, so there are various ways of describing the Lie algebra. So the basic idea is the following. Let's sort of informally speaking, not in a strictly mathematical sense. Essentially, what you have is this highly nonlinear surface, but it's smooth, right? So think of 3D rotations, right? You need 9 numbers. Because it's a 3 by 3 matrix, I need to specify 9 numbers to fully specify that matrix. But so it's essentially a point in R9. But actually, it sits on some manifold that satisfies the orthonormality constraints, right? So now what I want to do is actually ask the question, locally, what do things look like? Because I know that I don't have a global description of this representation. I want to look at the local representation. So locally, now there are various ways of describing the tangent space which is equivalent to the Lie algebra, and I'm not going to spend much time on this. There's a lot of structure here which we will just sort of state without really developing it in its fullest sense. You could ask, given a point, let's say on the manifold or the Lie group, let's say the identity matrix, I'm going to require that I find a mapping which is, I can find all mappings such that they form an equivalence class where the derivatives at 0 are the same. So in other words, essentially I'm at a particular point informally speaking, I'm at a particular point on the surface, and I want to know, I want to find mappings which allow me to move in different directions. It's nothing but describing the tangent space, which is essentially a linear structure there, okay? And that forms the so-called Lie algebra, which is essentially a vector space, but has certain special properties associated with it, okay? Now, so let's take a moment to try and look at a specific case. So remember our orthonormality constraint, which said M transpose M is an identity. Now let's say I just move a little bit away from it, right? So I move from M to M plus epsilon times some delta. I take a small step in some direction. But remember, these are matrices, right? So M and this big delta are matrices, yeah? So then in the limit of epsilon tending to 0, this relationship still needs to be satisfied, which imposes a constraint of this form on the elements of the tangent space, right? If I'm moving in the tangent space, then they need to satisfy this constraint, which basically means this, as I hope you will immediately see, is simply saying that the matrices delta, which are elements of the tangent space, have to be skew-symmetric, okay? So it induces a certain geometric form on the problem, okay? The next step that we will need in this machinery, I'm slowly trying to build up the machinery that we will actually use for solving our problem, right? So is this notion of conjugation. I'm not going to motivate it, I'm just going to state it as such. So there is this notion of conjugation, which takes two elements, G and X, and finds a mapping of this form. And it gives rise to this notion of an adjoint. I'm sorry, I'm having to rush through this because this is fairly involved, and we really just need the result from this particular form. We're not really interested in the actual structures at this point. Now, what it essentially allows us to do is ask the following question. If I were to take the adjoint operation, so imagine I'm at the identity element on the group, and I can take small steps around it, right? I'm in the tangent space, and so these are the higher order terms that I'm going to ignore, right? And now I consider another element y in the tangent space, right? And I take this adjoint operation. What do I get? Locally, around the identity, I can approximately write g as I plus epsilon x. And so therefore, this operation will look like this. Yeah? So now, typically, if you think of, for example, the so-called abelian groups, like for example, if you look at the standard vector space addition form, this is going to cancel out, right? xy is going to be yx. Yeah? So, but that's not true in our case, because what we are looking at are non-commutative spaces. So I hope you recognize that even without looking at the Lie group structure, we know that not all types of matrices are commutative, right? So A times B is not the same as B times A. Okay? And so that's, so in the case of the Lie group structure, so you know the non-commutativity is actually embedded here. Okay? And so this is known as the bracket or the commutator, and that it signifies the degree of non-commutativity, right? If this goes to 0, then you know that things commute. Yeah, you can just swap things around, right? So you can do A times B is the same as B times A. But that's not going to be true in general, okay? And that's where, you know, our difficulty lies. That's where the geometric structure lies. So I've already said this, so there is this Jacobi identity. We don't need to worry about that. So effectively, what do we have? What we have is we are interested in we are looking at the geometric structure of the motion group, and we have now recognized that they form special types of groups called Lie groups, so which have both a smooth Riemannian structure, or they're smooth manifolds, but also have group properties, right? But we also recognize that they are not commutative. The operations in this group are not commutative. Okay? So we need to be careful about how we do things in a non-commutative setting. So in particular, there's two special properties that are of interest for us. One is that the product is a smooth differentiable mapping, and so is the inverse. Okay? And so essentially we have nice smooth forms, but we need to just make sure we take care of the specific properties which deviate from vector forms here. Okay? Oops. Let me just go back, sorry. Okay, so if I want, so remember I said, let me just quickly remind you. Sorry about that. Yeah, so you have a local description here, right? I take a point on a sphere, let's say, and I put a tangent plane there. That's, you know, good enough locally, right? I have a good description of what's going on there. But this is no longer useful when I'm here. Yeah, so I need a different local description, and what I will need is a way of connecting the two in some sense. Okay? So in the case of Lie groups, this has a very nice special form associated with it. Where am I? Yeah. Okay. Sorry, I'm jumping back and forth. All right, so here's the basic problem. Remember, if I am at a point on a group, I can take a tangent plane. Essentially, I can have a vector, and that's a vector space with special properties, like, for example, the commutator bracket and so on and so forth have to be satisfied there. But, you know, think of a tangent vector, you know, sitting in that tangent space, right? Think of vector sitting in that tangent space. So that's now going to be tangential to the manifold at that point, right? So now if I want to move that somewhere else, remember I want to move my descriptions from one place to the other, it so turns out in the case of Lie groups, I'm not going to prove it, but it's not very difficult to see that, is that if I take a vector x in the Lie algebra at I, right, I take the identity element I on the group, and I take a vector in the tangent space or the Lie algebra x, and if I now apply an operation, matrix multiplication G to x, this vector is tangential to G. So in other words, I can take, if I'm at some point, I have a vector, I can apply a transformation, I can apply a matrix operation to it, move it somewhere else, and it's going to be tangential to that point there. Okay? And so that's very nice because then we can actually use this property to develop a very important formulation, which is the exponential mapping. So what it basically says is that it gives rise to this kind of a differential equation, right? So you can start at the identity element, and you have some parametrization, and so you move. So this relationship has to be satisfied from the property that we looked at. So which basically means that G of some parametric scalar S is going to be the exponential mapping. Right? This is an elementary differential equation, so this is going to yield this. So what this basically means is the following. If you look at this sketch here, what it's showing is that if I am at this point on the manifold, and I have a tangent space, and I have these two colored solid vectors in blue and green, which are two tangent vectors in different directions. As I move in this direction, the exponential mapping of, at every point here along this direction, I am in the tangent space, and I can find a direct mapping from that point onto the, onto the group using the exponential mapping. So what it's simply saying is that if I have this complicated group structure, I have a tangent plane there, but in any direction, however I move in the tangent plane, I can find its corresponding point on the group by a direct mapping, which is given by this exponential form. Okay, and I will develop that in a moment. We will see how it corresponds with much of our intuition about certain forms of rotation. But so the exponential mapping is key, and well, correspondingly, it's convergent everywhere, right? That's a standard result that we know. And remember, these x's are matrix forms. They are not scalars, right? These are matrix forms. Yeah. So you take exponential of a matrix form, you get a matrix. So you get a rotation matrix. You take a point in the Lie algebra of the rotation group at any given point. You take its exponentiation. It's going to give you a rotation matrix that satisfies the orthonormality constraints, right? That's by construction. Okay, so, and without going into too many technical details, the inverse exists, which is the logarithm. But obviously, the log is not defined everywhere, right? So, without worrying too much about it, in a local neighborhood about a point, the logarithm mapping allows you to go from the group to the tangent space. So you have essentially two forms, right? So you have the smooth nonlinear manifold, which is the Lie group, and you have a tangent space, let's say, some vector space representation, which is the tangent space form, which is the Lie algebra around that point on the group. And the mapping between the two is essentially straightforward. It's either an exponentiation or the inverse is the logarithm. So you can move back and forth easily, right? It's not, so the point what you should recognize here is that this is not a projection. So typically, for example, if you have, let's say you have a constraint, geometric constraint, and you're away from it, what would you do? You typically find a projection onto it, right? That's because that was an approximation and you just sort of moved it onto the geometric constraint. So this is not a projection operation, it's a direct mapping. And so it's exact in that sense, okay? All right, so what it allows us, what this basically means is that now we are in the business of trying to develop the notion of distances on groups. Because remember, if I want to do any estimation, I need to specify ways of defining distances between points, right? Without that, I cannot make much progress. So if you think of, in general, for non-commutative groups, this relationship is not true, right? E to the x times e to the y is not e to the x plus y. However, if I take matrices of this form, e to the scalar s1 times x and e to the scalar s2 times x, that's going to be commutative. And what is this simply saying? It's simply saying, as I move along in a given direction on the Lie group, I'm going to trace out a path on the group, which is given by the exponential mapping, and that set of points on the group will form a one-dimensional subgroup. And that's going to be commutative. Okay? And so what this will do is it will allow me to just induce a notion of a distance metric. So basically what I'm going to do is, if I want to measure the distance from this point to some other point here on the manifold, well, that's nothing but the distance. I will claim that that distance is nothing but the distance I need to move in the tangent space to get this mapping. Okay, so that gives me a natural way of measuring distances. And so in general, I'm not at the identity element on the group, so I want to measure distances between any two elements, x1, x2, and I will assume that the distance measure is so-called left invariant, that is, it satisfies this property. That is, I take x1, x2, I want to compute their distance, I can left multiply with x1 inverse, and I'm going to demand that this distance be preserved, and that's true in many cases. So if I do that, then I get this distance metric, right? And now, given that I'm computing the distance between the identity element and some other element on the group, and I've shown you that in this form and how to do that, we are now in business of actually saying we know how to compute distances between elements in the group. Okay? Right, so there is this business of left and right invariance. So just to restate it, if I have, so in standard vector spaces, it doesn't matter because things are abelian, right? So if I take distance of x1, x2, and I can add some x to it on both sides, and you're going to get the same answer. But that's not true in general for matrices or group forms of this kind. So left invariant simply means that if I left multiply the two elements with any arbitrary matrix of the same group, the distance has to be preserved. Right invariance basically says the same with right multiplication. And bi-invariance basically means both are satisfied. Okay? And so it turns out that for rigid rotations, the intrinsic metric is bi-invariant. But there's a proof, which is of key importance in disciplines like robotics, for example, which shows that there is no bi-invariant metric on SE3, which is on rigid motions. Yeah, with rotations and translations, you do not have a bi-invariant metric. And that has implications for how you do computations on that. But anyway, okay, so quickly, so what we have now said is that in general, Lie groups are not commutative, but in the neighborhood of an identity element, if you do a local expansion, then you can approximately write the exponential form. The elements are now going to be written in this form. So if you remember, we had, where am I? Yeah, so this is the exact form for the group element. But if I were to take a very small x, then I can ignore all these things, right? Which is what is essentially like a Taylor series expansion, right? So if I were to do that, then essentially products would commute. Right? Remember, otherwise you're going to get some other higher order terms with the brackets xy minus yx and so on and so forth. And we're going to ignore them because we're just going to move locally, right? So if you do that, essentially what you have is this, it starts getting close to this complicated business of defining ways of measuring distances, or rather transformations in this space. So we know that e to the x and e to the y is not the same as e to the x plus y in this case, because these are individual matrices and this multiplication is not commutative. But obviously e to the x, e to the y has to be e to the something, right? So if it were commutative, this would have been just x plus y. But now it's not so. It's something else. Yeah? So in the literature, in the mathematical textbooks, you'll find this BCH form, and it plays a key role. So you get basically a series form. Yeah, you get a series expansion. There is an explicit definition of what this term should look like. And if you notice, essentially, if your groups were commutative, then this bracket will go to 0, right? Because x comma y is nothing but xy minus yx, and that's 0. So all of these terms would disappear, and you would get back the standard form that we're familiar with in the case of commutative forms. But otherwise, that's not true. Yeah? So otherwise, you have this series form, but they're all going to be in terms of this bracket. So there are ways of doing this. So now this may look really daunting. You have this, this really complicated series of defining, measures of this defining forms of this kind. It so turns out, luckily for us, that for the groups of interest, which is rigid rotations and rigid Euclidean motions, there are closed forms for this. Yeah, so this series actually has closed form representation. Okay, so now just to make sure that we are on the same page, we are going to be looking at Euclidean motions, right? So a Euclidean motion is essentially going to be written in our case in this form, where the rotation is of special interest to us because that is itself another Lie group. And so that's denoted as SO3, the special orthogonal group of dimension 3. And the Euclidean motion is written as SE3, the special Euclidean group of dimension 3. And as we know, they have the following degrees of freedom, right? The rotation matrices R have 3 degrees of freedom, and the motion M have 6 degrees of freedom, right? 3 for rotation, 3 for translation. Okay? All right. So now let me try and intuitively develop. I want to make sure I'm on track with time. We started 15 minutes late, didn't we? Yeah? I'm just trying to make sure. I'm supposed to take a break halfway, right? So what's a good time? What do you guys think? Or I'll just go ahead and just then break at some point. Yeah? Okay. Fine. Okay. So so let's try and develop what we have written out in the abstract form in a simpler setting that we're familiar with, which is just simple, straightforward 2D rotations, right? So let's say I take a point xy and I rotate it by an angle delta theta. Yeah, it goes here. So and theta is basically this point is at angle theta with respect to the x-axis. Right? Pretty straightforward. So you can take these 2 points and write you can write the triangular form here and work out the trigonometry of what it should look like. It's very trivial, right? So I've just made an this is just for exposition. Think this delta theta is essentially a very small rotation, right? An infinitesimal rotation, right? So if you do that, then you can show that x prime and y prime, which is the new location of the point, has to satisfy this relationship. That's trivial, yeah? So I want, you can just check for this later if you wish. If you just take the first order approximations, you can actually now write x prime, y prime, which is the new location of the rotated point, as xy plus delta theta times minus yx, okay? That just comes from the geometry here, okay? And so you can rewrite this as x prime, y prime, that's the new location, is some identity matrix of size 2 plus delta theta times a matrix B, which is of this form. Okay? So far so good. This is very trivial. And this matrix B, I hope you immediately now notice this is skew-symmetric. Yeah? Remember we talked about the tangent space of orthogonal matrices having a skew-symmetric form. B is skew-symmetric here. Yeah? And B in particular has the special property that B squared is minus I, which we will use. You can verify that. That's very easy to check. Yeah? And now we'll say, what if we repeatedly apply small infinitesimal rotation? So think of any rotation of a point along a circle by an angle theta as essentially many small infinitesimal rotations, right, put together. Okay? So if you do that, so what do? You take the net rotation theta and you divide it by n. You take n rotations. Yeah? So then what is the net rotation going to look like? Well, it's just going to be the product of all these individual rotations, right? So it's going to be of this form. Because now this is, remember, we said this is my infinitesimal rotation, I plus delta theta times B. And now I'm going to apply it repeatedly, where now delta theta is theta by n, right? I've just taken the whole rotation and just chopped it up into small parts. Okay? And now this obviously has a series expansion. Yeah? So and notice that B squared is minus I. So what do you get? You get basically even and odd terms in your binomial expansion of this form. And in the limit, if you write those two series out, you take out the even and odd terms, you're going to get the standard rotation form that we're familiar with. Okay? So what this is simply saying is that the 2D rotation, which is of this form that we are all familiar with, essentially has a Lie algebra, which is just this B. Okay? So what it's simply saying is that R is exponential of theta times B. So remember we talked about the fact that you have a Lie group, you have a tangent space, and you have a specific direction. Well, what is the dimensionality of the tangent space going to be here? It's going to be the number of degrees of freedom that we have. Yeah, which is in this case just 1, because in 2D rotations you just have 1 degree of freedom. Right? So this, don't get confused with the fact that this is a matrix, but it's a matrix, but in your representation it's just a direction. It's a single direction. So it's a tangent space of dimensionality 1. And so as you move along that direction, you're going to be doing this exponentiation, right? You move by theta from the origin along the direction B. The corresponding group element is the exponentiation of theta times B, which is nothing but what we're familiar with. Okay? So this is just to give you an intuitive idea of what the group structure looks like. The one that we are interested in, which is 3D rotations, can also be worked out. So now think of, what do you do in 3D rotations? You pick an axis of rotation. In this case, for convenience of illustration, I've just picked it to be vertical. You have a point, and you pick an axis of rotation, and what do? You rotate, about that axis, right, by a certain angle. I mean, that's the standard. That's one way of defining how you rotate a point in 3D. Yeah. So if this is my origin, I pick some axis of rotation direction n. I'm at a point P. I want to rotate it infinitesimally by some delta theta. Well, which direction should I go? Obviously, it has to be in this plane defined by this circle, right? The direction in which you'll move is going to be in this plane defined by the circle. It also has to be tangential to the circle at this point, right? And so what you end up with is the fact that you can work out the steps, but that directionality has to now be orthogonal to P, right? Think of this, I have this vector from the origin to P, and I have this plane, and now it also has to be orthogonal to the circle on that plane, in the two-dimensional plane that I defined. So it has to be orthogonal to both P and P minus the projection in the orthogonal direction. And so that's going to be nothing but n cross P. Yeah? And so now what you have is P prime, the new position is just again going to be of this form. And this is just nothing but the skew symmetric matrix of the cross product form. And what you can then immediately show is that the rotation, again, if you take the limit, is going to be the exponential of a three-dimensional cross product form. Okay, and so that's the representation for 3D rotations, and that actually is the same as the well-known Rodriguez formula that some of you would be familiar with. Okay, so what it's simply saying in our case, excuse me, so the rotation group is sitting in R9, right? So you need 9 elements to specify it, but the tangent space, but it has only 3 degrees of freedom, so the tangent space is 3-dimensional, okay, in this 9-dimensional space, right? The tangent space is 3-dimensional, and that space is spanned by matrices of this, is spanned by matrices of this form. Remember, in the case of 2D rotations, you just had 1 degree of freedom and you just had one matrix defining the tangent space. And now you need a basis of dimensionality 3 to be able to fully specify the form that you're interested in. Okay? And this, I hope you'll notice, is nothing but the skew symmetric cross product forms for the canonical basis vectors, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. If you think of, that's your canonical basis in vector space. And now these are nothing but the cross product forms of those canonical basis vectors. Right? That's the structure of the group. Okay? So we will use a lot of this. You may be wondering why we are developing this, because we will use a lot of this machinery to be able to solve our problem efficiently. Okay, so I'm just going to, So basically, to summarize, you have the tangent space which is spanned by these 3 bases, and you can do exponential. So now given any, so remember, I hope most of you are familiar with this. So if I want to specify an axis angle representation of a rotation, what do I need? I need a direction n and an angle theta. And their product is, you would typically write as, omega is theta times n, right? And so that's going to say that I'm going to rotate about this direction by this magnitude of omega. Okay? And so that is nothing but basically finding the equivalent rotation form is nothing but the exponentiation of this cross product representation. And that comes directly from the group structure that we examined till now. Okay, so essentially you have, so by the way, I think I should have introduced this. So this particular form denotes, this representation denotes the tangent space or the Lie algebra for a given group, right? In small, SO3 is nothing but the Lie algebra of the group SO3, and SE3 is correspondingly the same for the Euclidean group. Okay, and the BCH form essentially allows us to now define distances between elements in this group. So the moment I define distances between elements of the group, I'm in business, because I can start doing some elementary statistics or some optimization, let's say. Because once I know how to compute distances, then I can define those operations in a meaningful manner. Okay, right. So let me now try and move to what we are interested in. We are only interested in the group structure. Yes, sorry.
One question. The developed exponential mapping were about the identity. So the tension space is basically at the identity. How can we guarantee that this also behaves at other places in the manifold?
So it comes from, good question. So what we are going to do, so we're going to use 2 elements. So if you recall, where were we? Right, so this is the key element that I didn't develop fully, basically, in the interest of time, is that we know that if you develop the tangent space about the identity, developing it about G is nothing but this translation. So that allows us, that's only one part of the story, that allows us to do these operations easily. And the other part of the story that we will use is this, that's a very good question that you asked, is the left invariance of the metric. So if I want to compute distances, maybe I should have developed this much more systematically. If I want, this is what I'm interested in, right? I want to know what is the distance between two elements in the group. So what I'm going to do is I'm going to use left invariance. So I'm going to say that my distance metric has to be left invariant. I'm going to demand that, and it's true for the ones that we have. So then left invariance simply says if I pre-multiply by any element, I preserve distance. So in particular, I'm going to pre-multiply by x1 inverse. So that gives me this distance, right? And so now I'm in business, right? Because now I can actually, yeah? So what I'm doing is essentially, if I'm here, I kind of, in some sense, move the whole thing around till one point comes to the identity, and then I'm in business with the one-dimensional subgroup that's of interest. Yeah, that's because we are only interested in measuring the distances at this point. Yeah, I hope that's clear. Yeah.
Thank you.
Okay. So, all right. Okay, so now let's look at what we're going to use this for. So we all know how to do averages in vector spaces. This may look really trivial to you. You may be wondering why you're sitting here in this room, right? So if you want to take the mean of points on a plane or in vector space, well, just take this operation and you're done. And so this blue point denotes the arithmetic mean of this red set of observations, right? The question is, will this work with nonlinear spaces? The answer should be obvious, no. So imagine you have points which lie on a circle, so that's your geometric constraint, right? That points are on a circle. You can do stuff like saying, well, okay, I'll just pretend that they're not on a circle, take their mean, which is going to be on the middle of the chord, and then just project it back onto the manifold, which is the circle. And that's easy to do here, right? You can see, just take their mean here and then just push it back onto the circle. That's going to satisfy the constraint of being unit norm. Yeah? So maybe it's not too much of a problem, and then now you realize that as the points move further and further away, you're in trouble. For example, in this case, yeah, when you have 2 points which are antipodal, you have 2 solutions which are equally good, which are like the so-called means, if you will, right? So the question is, you do not have a unique definition of a mean anymore, okay? So the basic lesson here is that you have to be careful about how you do any of these notions of averages. So many of the things that we are familiar with vector space operations that we take for granted do not translate very easily to the representations that we have on hand. So this is a very trivial example that I'm showing you, that of just points on a 2-dimensional circle, and you can immediately see that you can get into trouble. Yeah? Excuse me. So, in other words, another way to think about it is if I give you 2 rotation matrices and I take their arithmetic mean, that's not going to be a rotation matrix in general, right? That's not going to satisfy the orthonormality constraints that I want them the mean to satisfy, right? So if I have 2 measurements of the rotation of an object and I want to find the average, well, the average better satisfy the geometric constraint that it represents a true valid rotation. And the question is, how are we going to do it? So the way I showed you here is what is known as extrinsic averaging. So what people do is just simply pretend that the constraints don't exist, work in vector spaces, and then map the solution back onto the constraint set that you want it to be satisfied. The one example that you may be familiar with is the well-known 8-point algorithm in epipolar geometry estimation, right? So you just solve it linearly, ignore the rank constraint, and then just simply impose the constraint back later, okay? It kind of works reasonably well for when the noise is small, right? So if it's here, it's okay. It's not a bad solution that you can get. But if the noise, if you will, or the difference or the degree of inconsistency is high, then you're going to start getting into trouble if you do stuff like this, right? So what we are interested in is we want to work on the geometric representation directly. We do not want to work in this extrinsic averaging sense. We want to work intrinsically on the manifold. I mean, that's the whole reason to develop this whole complicated machinery for our purposes. Okay, any questions at this point? Okay, so what we want to do is develop a notion of an average, in this case for rotation, such that it is still on the group. Okay, and what I will show you now is how to do this using the Lie algebra. So let's go back to our old friend, which is the mean of a set of points. So the mean is just given by the straightforward analytic form, but you can also think of it as a variational minimizer, right? So you want to define the mean mu, which minimizes this cost function. And of course, if you do calculus, you will immediately get this as the answer. But let's bear with me for a moment, and then let's ask the question, what are we trying to do? We want the mean such that the sum of the squares of the individual distances to the observations is minimized, right? That's our objective here, yeah? So you could think of it as doing, say, gradient descent, right? So you could do gradient descent to solve this problem, yeah? So you start somewhere, and you take the gradient, which looks like this. You take some step, and you move, yeah? So remember what we said. In the case of vector spaces, wherever, you can pick your coordinate system anywhere you want, and globally you're describing the entire space, right? In other words, if I want to look at these differences, this difference vectors, xi minus mu, that's a vector. That vector is independent of the choice of the coordinate system in which I represent the points to start with. Yes? But that's not true anymore in the case of the groups, because your representation is only valid locally in the tangent plane. Yeah? So what you will need to do in the group, in the case when you want to do similar kinds of averagings on the Lie group, is to recenter the origin, if you will. Right? So you want to move the origin to wherever your mu is, and then rewrite your representation. Okay, so because that's the local tangent space expansion is only valid, locally, right? And that's the whole idea. Yeah? So that's the essential difference. So the motivating idea is just this straightforward thing, but with this little trick that you introduce this business of moving your entire coordinate system to where you currently are, so that you can actually solve the problem in a meaningful manner. So just to reiterate, so you can define averages. So in this sense, so we did the variational minimization. You can define other distance metrics and get other solutions. So the extrinsic average, if you will, as we saw in the case of the circle, is simply saying embed the points in the vector space, pretend that they're in a vector space, take their average and project back. Okay? And what we are interested in is the so-called Karcher mean, which is simply saying find me an x in the group which minimizes this cost function. Right? This looks essentially no different than what we did in the vector space case, right? It's simply saying minimize distance square, the sum of squares of distances, except that you need to be careful about how you are measuring these distances on the group. Yeah? And so in general, this is very hard. For most Riemannian manifolds, you do not get easy solutions for this problem. But in our case, because the group structure has this exponential mapping, you can actually do it fairly easily. And that's what we're going to do now. Right. So I'm just going to jump straight in the interest of time. I'm going to do the following. So I'm going to start with, remember we did this left invariance business. So you want to compute distance between x and y, and you rewrite this with using left invariance. And then locally, it's nothing but the logarithm of this element, remember, because you're measuring distance between elements by recentering it around the origin, and then looking at what its representation looks like in the tangent space in the Lie algebra, right? So if you look at this logarithm of x inverse y in this case, approximately it is nothing but the vector space difference in the Lie algebra, right? Up to a first order approximation, this is true. Okay? And remember that the Lie algebra is a vector space, so you are allowed to do that. And so then now you are in business, you have an algorithm for computing the average of a set of elements of a group intrinsically, right? You are always on the group. So here's how you do it. So what you do is, well, basically you run this algorithm, but let me try and explain what this does. So what you do is, so this is, remember the gradient descent business that we looked at, right, for computing the mean of a set of points. So just try and follow that analogy here. So you start, your input is a set of elements of the group, x1 through xn, and your objective is to find a mean of those elements of that set. And so you initialize somewhere, in this case you could just initialize it with the identity, and then you subtract the mean from the observations. This is subtraction. And then you move to the, so when you subtract this, notice what this is doing. This is essentially saying, I'm recentering my identity at my current mean. You know, I mean, that's going to be my new identity, right? I mean, I'm recentering my representation to be at the current mean. And then I'm going to move to the tangent space, and that's a vector space. So I take the average in the vector space, and then I exponentiate back. It allows me to come back to the group. Okay? Any questions at this point? Okay, and once I do that, well, I'm going to update my mean. Remember, if you take a gradient descent step, you just add it up. This is nothing but adding it up, but notice the ordering that's important because of the non-commutative nature of the form that we are looking at here. Okay? And so you can repeat this till convergence. And you're going to, and remember, this step here involves a first order approximation of the distance metric, but at no point are you non-intrinsic. You're always on the manifold, right? You move, you take differences, move to the tangent space, do your operations, vector space operations, which is taking averages in the tangent space, and then you map back. And then you keep recentering, and that's your new origin. You move your origin there, redo it till convergence. Okay? Now, so you'll notice immediately that there are some essential differences from the standard vector space things that we have been familiar with. And what the main question that arises here really is the convergence of such operations, because this is essentially a non-convex optimization that you're doing. Okay, so we won't go into the details here, but basically there's a proof by Manton in 2004 where essentially he develops it for matrix group forms, and basically what it translates to in our case is simply says, if the individual elements xi's are not too far from each other in some strictly defined sense, it's related to the sectional curvature of the manifold, if you're familiar with that idea. But if you're not, it just simply basically means that as long as points are not too far from each other, this iterative method is guaranteed to converge to the optimal solution. Okay? If things are too far away from each other, then that's not true anymore. Okay? So you did not have this problem when you're dealing with vector spaces, because you can move in whatever manner you want, but that's not true anymore. Yeah? Okay, so our next step then is to ask, averages is not what we want to do, right? Remember, you might have forgotten by now because we've looked at so many different things, but our original objective was to give in a set of edge observations to reconcile them so that you figure out what the individual values of the vertices are, right? And so you can So your problem is now of this form. Given individual relative motions mij's, you want to find individual, this should be an m, I'm sorry about that, individual camera values mi's, which is consistent in the best possible sense according to this cost function. Right? That's the fitting that you're trying to do here. Okay? And so we could do the same kind of iterative averaging. Okay, so let me just do this. It's the same idea that we did for the individual. So remember, what we did just now is take individual just elements on the group and average them. Now what we're going to do is try and solve the problem of trying to reconcile the values of the edges that we had on the graph and get the individual values of the vertices, which is the averaging problem that we are interested in, the so-called motion averaging problem that we are interested in. Okay, so you start with essentially what it translates to is the following. You want to minimize this cost function. You want to find individual mi's which are on the group. And you want to minimize this cost function in a meaningful, consistent manner. And this distance is nothing but the BCH of this form and so on and so forth. And you can just translate this into the Lie algebra just the way we did for the individual averaging case earlier. And then you can, so notice that essentially you can rewrite, so now you're in the Lie algebra and these are matrices. So for example, if you're looking at rotation matrices, that's going to give you the difference of two skew symmetric forms, right? Because those are cross product forms. Think of this as omega j cross and omega I cross, right? Is equal to omega ij cross. I mean that's just nothing but a linear system of equations, element wise. Yeah? So because there are only three individual relationships that are actually there embedded in those two, in that matrix form. So now if you extract those parameters, you get a linear system of equations, and voila, we know how to solve this. We did this a little while ago, right? So what that translates to is you solve, so basically what we are doing is doing something analogous to what we did in the case of averaging individual elements on the group, which is the following. So let me restate what we are doing. We're currently at some, so remember this is an iterative process, right? So we are at some solution for the individual vertices, which are these camera values. So I'm going to do essentially look at the group structure expansion, the tangent space expansion about these individual points. And that's going to lead to a linear system of equations that we saw in the vector space case. Okay? And then if I solve this, I get my next step, and I can iterate back. So essentially, this is the algorithm for doing motion averaging on the groups. So what you do is you're given a set of individual inputs, right? And which is the relative motions, and you want to find the cameras that correspond to these relative motions in the most consistent fashion. Well, this is just doing the same thing again and again. So it's the same thing. So this form, notice because of the non-commutative nature of matrices we are doing, this is essentially nothing but mij minus mj minus mi, right? That's what it is, except that it's done in the correct, consistent fashion. And then you take the logarithm, so you map it into the Lie algebra, and you extract the relevant individual parameters, and you get a linear system of equations that you solve in vector space. And then once you get the solution, this is telling you how much you should move in the Lie algebra. Therefore, this is how much you should move in the group. And so you exponentiate back and you update your motion individual camera matrix, well, again, till convergence. Okay? And notice what I did here. I left this in red. I didn't tell you how to solve this. I just said solve the system of equations. And you can think of, well, for now you can think of this as, well, it's a ax is equal to b problem. You can think of just solving it linearly, right, a least square sense. But we'll look at various other ways of doing it. And so I'm going to wrap up this section and then we're going to take a break. Yeah. So this is the algorithm, and essentially you'll notice A is nothing but your original incidence matrix, and it's related to the graph Laplacian and so on and so forth. But the key point to remember is that A is sparse. A has only entries of plus or minus 1. And so when you say A times some vector, that's not a multiplication operation, but it's actually an addition, right? Because your entries are just plus minus 1. So that allows you to do certain computations very efficiently. Because remember, A is going to be sparse, but A is also going to be very large. Yeah? If you're taking very large sets of cameras, this is going to be a very large system of equations, but it has a special structure that we can exploit for our computations. Okay? Okay, so here is the reason I left this in red, is that the key issue in many intrinsic motion averaging algorithms, the key difference is only in this step. It's really just how you solve this particular step. So my original formulation a long time ago just solved this linearly. Then Hartley's group proposed a distributed approach for solving this, and I'll show you that in a moment. And then some years later, my student Abhishek and I showed that you can solve this robustly because you can have outliers in your data, right? So you can solve this robustly using IRLS, for example. Okay, so your key difference in, you'll see all these different algorithms in the literature, but really they're all doing the same thing except that they're solving this step differently. And it has different implications on the quality of solution that you're going to get. Okay, so in the interest of time, because we kind of started late, I'm going to skip issues of convexity. So there's some very nice, it's generally a hard problem to analyze because you're looking at a non-convex problem on SO3s, and there are issues to do with convexity. I'm going to skip this part, but I would encourage you to read these two papers, Hartley's survey in 2013, but a very nice paper by Kyle Wilson and others a couple of years ago, which said, when is rotations averaging hard? Okay, so it's asking the question, yeah, so you have this nonlinear optimization problem. When is it easy to solve and when is it easy to, when it's not so? And the sort of, the summary answer really is that what really determines is the interaction between the noise in your individual observations and the Laplacian of the underlying graph structure that you have. Okay, and so that determines the difficulty of solving this particular problem. Okay, so before we disperse for a short break, I'll just very quickly go over the distributed averaging approach that Hartley and others proposed. Remember, I said that essentially we are interested in solving this step. You can do it linearly. Just take, pseudo inverse of A times this and you're done. But that's going to give you a least squares solution. That's